6, 10. Perfect. It's recording. Bro. All right. Welcome everybody to AMACSS's first review seminar of the year. My name is Edison Pham, or you can call me Eddy. Today I'll be doing a review seminar for you guys for C11 Term Test 1. Because I know that you guys, I think you guys needed this. Because or rather this semester, I don't think there's a lot of practice questions given out. So this whole seminar is going to be like dedicated to just practice questions. If you have any questions, you can always just ask me. Otherwise, let's begin. So I'm pretty sure you guys already know what AMACSS is, so I don't think I should bother you guys with any of this. All right, let's start with the problem set. Select the correct statements regarding ML problems. So let me see. Let me try to put, whoops. Let's see. Crop this. So you guys want to give this a shot? Can anyone tell me if the first statement is correct? Stock price prediction is unsupervised learning because we don't know the future values. Is this true or false? Oh, the chat's. Will the notes be posted? I will post the notes as well as the answers at the end of the review seminar, as well as send it to Irene. Anyways, the first question is false and such. Any more answers? Yep, you guys are right. It's false. And the reason why stock price prediction is not, wait, hold up. I wrote is unsupervised learning. Yeah, so the reason why it's not unsupervised learning is because you can basically train, sorry, my mouse is freaking out. Give me a second. And the reason for this is that let's say you have like a time series, right? And let's say in each one of these cells, and you're trying to predict this value, you can train your model to base its current prediction, which is like a given label. You know what this is based on the previous two inputs. So in that sense, it's not unsupervised learning. All right. Linear regression can take in categorical features, true or false. Any more answers? Can anyone explain why it's true or false? Anybody have any justifications?
I think like as long as the features they're kind of ordering, I think.
Sorry, I can't hear you. Your mic is not clear.
Oh, is it working now?
Yeah, it's working.
Well, I mean, like I think as long as the categorical features they have kind of ordering, then you should regard it as regression, right?
Yes. Another thing you can do is if you have like, let's say your labels like 1 and 0, just to keep it simple, right? These are labels, not numbers per se.
Oh,
So
okay.
what you can do is that if this one, let's say this is feature regression is when the continuous, the input is, yep. As long as there's an ordering, feature is continuous. Did she teach you that?
I think the ordering is covered. But like what if like the categorical they're not like without ordering, then it's like not regression or
Oh, okay. Because what I had for an answer is that you can just do one-hot encoding. So like if this is label one, sorry, if you have just feature one here, then you can turn this into like two features, feature one, sorry, feature I one, feature I two, and do like one-hot encoding. So if this is like A or B, then you can turn like this could be like A or B, then this could be like one if it's A and zero otherwise. And I think you guys get the point. If it was B, it would be like encoded as 1, 0, etc., etc. Question 3. Extracting cars from an image is a clustering task. True or false? This is not a trick question. Any answers? What does extracting mean? Oh, sorry, if it's unclear. Let's say you have an image, right? And you're trying to determine if there's a car. Actually, you're trying to determine, it's kind of worded incorrectly, but you're trying to literally extract the car from the image and you get like the blob as itself. Yeah, sorry if it's unclear. So is this true or false? Yep, you guys are right. It is true because the car's not really labeled. You kind of have to just pull out the car from the image. I mean, that's the definition of clustering task. Training an AI model to play chess is unsupervised learning. True or false? Yeah, you don't have labeled outputs. Did I say, oh no, you're answering it. My bad. Any more answers? Yes. Reinforcement learning is what this task is. It is not necessarily unsupervised learning. All right. And finally, predicting whether an image is a dog or cat is a classification problem because our inputs are categorical features of the animal. True or false? Any more answers? That's correct. It should be the outputs, not necessarily the inputs. All right, perfect. Let's move on. Actually, I don't think I need the whiteboard. Question 2. What is the experience E, task T, and performance P of the image denoising problem from assignment 1? Does everyone remember that one quote where it's like this something something experience E task, and then there's like a performance measure? I think that was in one of your practice questions that Irene gave out. Also, this was original image, MS, sorry, P measure. That's correct. The performance measure is the MSE. Um, sorry, I didn't read the other ones. Experience. Yep, that is the clean image. Denoised image. That is not necessarily correct.
No, excuse me.
Yes,
I just had a question about the previous question.
yes,
The one where it talks about extracting cars from an image as a clustering task.
yes.
So in that question, is the task itself looking at a bunch of images and deciding if they have cars or not, or is it looking at one image and taking out the car from that image?
Looking at an image and looking at one singular image and applying a clustering algorithm to extract the car.
Okay.
Okay, so it seems like everyone got E and P right. How about T? Is the experience just the input? The experience is the label. So in this case, you're comparing the actual output, which is the original image, the the denoised image. The task, I don't think anyone got it. The task is denoising the image. Yes. Yeah, I think that's correct. Yeah, perfect. And this person said it before, but anyways. Suppose you build an AI model to predict any possible handwritten decimal number. Your output space seems to be continuous However, explain why this is not a regression problem. Does anyone know why this is not a regression problem? Even better yet, can anyone tell me, this is kind of not taught in CLM, but can anyone tell me what this type of problem is, if you guys know? We are not comparing their orders. That is correct. When you try to detect like handwritten images, there's not really any notion of ordering when you are trying to detect what the handwritten, not digits, but the decimal number is, because there's no ordering relations between them. So let me see. Pull up the whiteboard. In regression problems, I think she should have told you this, but there's like two conditions. The first condition is that your outputs needs to be ordered uh from an ordered space. And second, I think it needs to be numeric. This is the conditions for a regression problem. Yeah. So your outputs needs to be they can be ordered and they need to be numeric. It happens to be the case that yes, our labels in this case are numeric, but they're not necessarily ordered because there's not really any order relationship between different handwritten decimal numbers, right? All right. And finally, why do we often use MSE over MAE? In other words, why do we square our residuals instead of taking the absolute value? So just answer this first and then we can go to the next one. Take the Yes, that is correct. It is easier to take the derivative because when you try to differentiate an absolute value function, you have like a lot of issues because it's not smooth everywhere. And what is the trade-off of doing this? Actually, hold up. Yeah, never mind. And what is the trade-off of doing this? Increased value of error. Sorry. Uh, what do you mean by that? The increase of value is the same as the increase of error because if your MSE goes up, the value of your MSE goes up, then your error goes up as well. Pronounced. So you mean like MSE is more sensitive than MAE? That's correct. Do you know the reason why that is the case? Yes, exactly. You square the values, and if you have like, so this is your, this is basically your MSE. Let's say you had like a very large residual, right? This is gonna get like squared, which is very, very bad if you have like very obscure outliers from your data set. All right. It can also have, it says, right, if the difference is less than one. Yes, that is also correct. It can also have the opposite effect when the difference is less than one. All right, next page. So, true or false? Decreasing dataset size mitigates overfitting. Any explanations why it's false? Overfitting is mitigated by increasing data size set as well, because a model can fit well. Mitigate. Decreasing data. Well, yeah, I think you guys understand it pretty well. So to your point, it's easier to come up with a model to fit all the data. Yep, that's correct. All right, next question. Increasing dataset size mitigates overfitting. True? Can anyone think of like a counterexample to this? Lucy is correct, not necessarily. Can you think of an example? Like an example of a case where you increase your dataset size. That's important, your dataset size, but it still overfits. Gary is correct. Because sometimes when you add data to your dataset, it might not necessarily be good data. It could be extremely noisy data, and that could potentially cause your model to not necessarily catch the important features, important what is it called? Yeah, the important features of your data set. All right. Which of the following is a sign of underfitting or overfitting? So let's start with the first one. Is the first, so what can you say about the first one? High training accuracy, low test accuracy. Yup, that is correct. Because I'm pretty sure you guys know why. So I'm just going to move on. What about number two? Low training accuracy and high testing accuracy. Luck. Yeah, exactly. This one is actually a really rare case. You'll almost never run into a low training accuracy and high testing accuracy. If you ever do, then yeah, exactly. Alex is correct. It's a bug. It's a bug in your model. You should go probably fix it, I hope. How about high training accuracy and high test accuracy? What do you guys think? Right model. Yep, that's correct. Neither. Exactly. It's the perfect model. Not necessarily perfect. You can't really make a perfect model. That's pretty impossible, but you have a pretty good model. How about the last one? I'm pretty sure by elimination, you guys can guess what this is. Yep. Yep. Underfitting. When your training accuracy sucks and your test accuracy sucks. Perfect. Compare overfitting and underfitting in the context of kin. And for this question, just tell me what overfitting and underfitting is in kin and regression. Don't necessarily compare them. Yeah, I kind of worded this question very badly. Let's start with KNN. Yep. K too small leads to overfitting. And the opposite effect is true when K is too large, it begins to underfit. Yep, that's true. How about for regression? What is a sign of overfitting or underfitting in actually I think yeah, we already covered this previously. Simple models cause underfitting, too complex models cause overfitting. Sure. Yeah, for the most cases, yeah, that's true. Yep. And just to compare them, usually how we would detect regression is overfitting, underfitting is like what we discussed in the previous question. But for KNN, you don't really have like a training set to work off with. You just have the test set, I guess, or the whole entire data set to evaluate whether your K value is correct or not. So that's kind of like the difference between them. All right. What are some ways to mitigate overfitting and underfitting in regression?
Sorry, I had a quick question. Could you explain how it
I
would
believe I
work?
wrote down three ways to do it. I'm sure there's like a lot of more ways to mitigate overfitting, underfitting. The lambda thing. Can you elaborate on the lambda thing? Sure, sure. Go ahead, Ishika. Which part of the KNN? So like how it underfits and overfits? It didn't. I tried unmuting, but I guess it didn't work. So when your K value is small, it begins to overfit. The reason for this is that it only looks at the closest neighbors. And what if that closest neighbor happens to be like an outlier? Then that outlier would have its own like whole entire region. Let me draw this out. Let's say you have this, where is it? Reset this canvas. So let's say you had a bunch of data points right here. But then let's say you have an outlier right here. Then if you were to have like a point, let's say right here, and mind you, this point is completely irrelevant, and imagine there's like a bunch of more points over here, more points over here. I think this would this would classify as this point instead. Yeah, even though the image doesn't seem like this is close to this and this, just assume that this is the closest point to this point. When in reality, we want this to be classified as these points. Make sense? And the opposite effect is true when your K is too large. It begins to underfit because it generalizes too well. It gets the whole entire thing. Does that make sense now? All right. I think I'll just move on. Anyways, yeah. To mitigate overfitting, underfitting, one thing you can do is you can either tune the lambda thing, as some of you guys said, the regularization term. By decreasing it, you basically, by increasing it, you mitigate overfitting. Where and also another way to mitigate overfitting, underfitting is changing the number of basis functions. Remember, if you have too many basis functions, your model is way too complex. And it begins to overfit, so you want to decrease it. And three, you add meaningful data. So not necessarily noise data, but like meaningful data to your data set. So this is where I kind of tricked you guys in this question. It says increasing the data set mitigates overfitting, not all the time. But it's the case if you increase it with meaningful data, it does help because it introduces more variability. Not variability, it's the wrong word, but like more features to your data set. Suppose one of your features has high variance. Is it a good idea to remove this feature? Also, Gary, yes, that is true. I'll get into that, I think in the next one. No, the one after the next one. Is it a good idea? Dropping unrelated features does help with overfitting. Thing is, for Canon, thing is, if you have a feature that is completely uncorrelated to the other data, then it is a good idea to remove it for accuracy purposes. I'm not sure if it's like an underfitting or overfitting thing. For Canon, how do we go about finding a good K? That's a good question. I think the rule of thumb, although I tried doing this and it's pretty bad, you take the square root of n, the number of data points in your data set. But personally, I wouldn't do that because I tried doing that in um one of my bootcamp lectures, and that was pretty bad. Yep, it's literally just trial and error, unfortunately. But I'm pretty sure there has been research papers written about this. I'm not sure. You probably have to go on the internet and search it up. Anyways, is this a good idea to remove the high variance feature? How do we decide? No, baby. Yeah, so I'll come to your question a bit. No, because with that high variance feature, yes, it might have high variance, but it could still contribute greatly to your, it could be like highly correlated to the other features and the output as well, to predicting the output. So no, you shouldn't do that. Maybe what you can do is like you can threshold some of the values. Just adding meaningful data help with fitting, underfitting. I think it helps with mitigating overfitting because if you add more meaningful data, then you're basically introducing like more features per se to your data set. Not necessarily the features you're using to like for your weight parameters, but like more intricacies to your data set per se. Can I say high variant data can still be meaningful? Yes, I think yeah, you could still say that high variant data is still meaningful as long as it has, so we should not remove, yeah, we should not remove it. Or what if it was like the only, think about this, what if it was the only, you have like very little number of features, and then you happen to find through like statistical analysis that this high variance feature has high correlation to your output, then you should definitely not remove it. All right. Okay, the next question. You have a time series of length 1000. Oh, by the way, this question I made up myself and it was from something I experienced at work. So that's just for reference. You have a time series of length 10,000 consisting of a person's brain activity measured in hertz from 0.1 to 100. However, some of the entries are missing. So you formulate the plan to impute them. You generate a dataset by sliding a window of size 5, using the middle value as the target and everything else as your feature. Finally, you train the model using simple linear regression. What are the several issues with this method? So let me show you. You only, whoops, you only have one long column vector representing like a time series, right? And they're all indexed by some time. We're basically sliding a size 5, is that 5? Yep, that's 5. Size 5 window across it and collecting features. This is your target value. These are your features that you're using to predict this target value right here. And you created like another data set with it. So you have like the following. Like a bunch of your O's here. You have X's, so forth. Does that make sense? But then you have like some of these entries are missing. So they could be like consecutive missing entries, etc., etc. So can anyone explain to me what are some of the issues with this method? Sensitive to noise. This seems like KNN. Not really. This seems like. And sometimes we have less data points. Anyways, can anyone you're only oh, you're not sampling 5 points. You're creating like a whole entire data set. So you're sliding this. This is your window, right? This is your window, and you're sliding it through the whole entire time series like this. You're just sliding it all the way to like the end. And each time you slide it, you collect like this row data. You're not necessarily sampling 5 points. You already have the points. Wouldn't this work if the data is linear? What do you mean by linear? Missing local features. Missing local features? So are you saying that, sorry, give me a second. Are you saying that if we happen to slide over this window, then we have missing features? I think that's what you mean, right? Yeah, you would basically run over these missing features and you kind of have to mask them. So if you have to mask these features, then that presents you a lot of problems. Because when you mask them, you're assuming that these are like basically the same label. Let's say we mask them as like -1, -1. What if this was um like a high value or like 0.1? Then labeling them as like -1 is extremely problematic. That's like one of the issues. Another issue is that um sorry, a second. Notice that linear regression does not account for dependencies in time. So basically when you're doing this, it doesn't really make any sense, right? It doesn't really have a way to keep track of the positions that each of these features has in affecting X. Another issue is that you're using a very small window. Remember, mind you, this is size 10,000, and you're sliding a window of 5 over it and trying to like predict labels based on that. Mind you, that is not a good idea. All right. And don't worry if my explanation is unclear. I'll post all the answers later at the end of this seminar. For this question, I'll give you guys like, is 10 minutes enough? I'll just give you guys like 10 minutes to do this question. It's going to be pretty long. Um, not, what do you mean by like too much task? I'm saying like if we slide a 5 window inside of a length 10,000 time series, then we're only, by small window, what is the disadvantage? By small window, so let's assume that our model somehow has the ability to like keep track of time. So that is not the case with linear regression. That's like one of the problems. But let's say it does. Then you're only tracking time dependency on like a 5 window. Meanwhile, for a time series that is 10K entries long, features at the beginning, near the beginning, have significant impact on features in the middle. Like, and features at the very end sometimes have significant impact in the middle. So that's one of the issues that this model we created has. It does not, it has way too small of a window. All right. All right. I'll give you guys till say 7:52 to do this question. So 10 minutes. 7:52. No, I mean 6:52. 6:50. All right. Wait, sorry guys. I want to ask, how long is your midterm for Friday? 1 hour long? 1.5 hour? Wait, so which one is it? 1 hour? Jeez. I pray for you guys. She might. Yeah, I don't want to spread some pessimism, but yeah, you would get. I don't think she would give you something this long, but like something similar to this. Yeah. If she gives you guys 1.5 hours, then it's light. You guys don't have to worry. She said map's gonna be on there for sure. Yeah, I'm not sure if she's gonna make you proof this. I don't think she will. Irene's pretty nice. She won't make you do that. Oh, that's good. because I took C11 last semester, and let's say I didn't like a lot of the class average was like a 39% because it was too short, or rather, the time was too short, but the exam was very long. I don't know the exact number. It was a C plus, but that's because she curved a lot. There was like severe curving, and the assignments carried pretty hard. What is a super tough final exam? Or uh, I'd say term test one was hard. Term test two was she gave us an extra 30 minutes, so it was good. It was good. But the final exam, let's not talk about that. It was very bad. Yes, she does curve. She does. I'm not entirely sure. I didn't, yeah, she didn't really post like what the class average was for the final exam, unfortunately. Oh yes, yes, yes. It was 50% weight. Five minutes left to do the question. All right. Was anybody able to prove it? Anyone in chat? Ooh, geez. Don't worry, guys. We did this in sure. I'm struggling with it. Yeah, no worries, no worries. I'll go over it. I think I'll just hand wave a bunch of stuff for the interest of time, but it'll be stuff like you guys already know. So let's say you did the proof, and then you have to show that this, your ridge, um, actually, is this correct? Sorry, your ridge regression solution would be equal to the following: x tilde transpose. Pretty sure you guys already know this, just from lecture. Tilde transpose y. And how do we do this? We have to recall like this formula right here is your loss function, whoops, for ridge regression. Oops. Does anybody not know how to optimize this? Because if somebody doesn't know how to optimize this, then I'll probably just do it. Anyone doesn't know how to do this? Okay, perfect, perfect, perfect. All right. So you guys should know how to do this. And I think if it's in the notes, you can just assume this if she were to ask you. As for the map estimate, wait, she also covered map estimate, right? Okay, then, so I'm just gonna like review it for a second. We're conditioning y on x tilde because x is observed, by the way, and w is your parameter. If we skip a bunch of steps, we're gonna get this is proportional to like x, the exponent of -1/2 sigma, sigma from where we sampled the x, the norm of y minus x tilde w vector squared minus 1/2 to identify the distribution of y first. Yeah, that should be one of the steps. So to do that, we can do that pretty easily because this is a linear combination of normals, correct? So what does that mean? It should be a normal, where we assume this to be a constant and EI. In linear regression, we assume this part to be like a constant, where EI is your distribution. I know it's a little weird here where W vector is a constant, but here's not. Actually, it is also a constant because we're conditioning on x tilde and W vector. So yeah, that makes sense. So literally all you have to do is just take the expectation of y of Gaussian. No, she wouldn't. I think for the final exam she did because there was a lot, but she she said for my behalf, no, she wouldn't give. We have to remember it. Even the multivariate one. It's pretty important. I can write it for you after. Just remind me. You'll get, because this is a constant, right? Then why not just bring it out? Still I. Plus the expectation of EI. What is that? That is 0. So this is your expected value, your mean. The variance of yi is equal to the variance of w vector transpose xi tilde plus epsilon. This is a constant. So what you can do when you have the variance of a constant is the same as epsilon I, right? Because shifting the variance doesn't really change the variance. And what is this? Sigma squared. So that's where we get sigma squared and the mean as such. Whoops. As such. Make sense? Don't want this to overlap. Yikes. Anyways, I'll just continue off from where I left off. And then for this term, this came from the maximum likelihood. this came from, actually, this is the maximum. Yeah, I think I wrote it wrong. Yeah, I wrote this wrong. The W is supposed to be like right here. Yeah, I wrote this incorrectly. It should be like P of W vector given your data. Your data is like X tilde comma Y. Oh, shoot. Uh, yeah, yeah, you're correct. This is your likelihood. So, give me a second. Bro, this is so. So just to be correct, W given Y vector, and this would like index from the whole data set, X tilde the whole data set as such. So this is be correct. It's proportional to, let me write the last term, W vector squared, like that. And this comes from your prior. This term comes from your prior. If you take the log of this, the log likelihood, the negative log likelihood, you'll get 1 over 2 sigma squared norm y minus x. Oh, what's the difference between the variance alpha? Variance equals alpha equals variance I. Sorry, your likelihood would be P of y given xw. Is x not part of the evidence or data? What do you mean by that? Because we need it to be in the likelihood so that this x right here is like a constant, right? Because it is a constant. We need this x value to be a constant in order to do this expected value thing and the variance. Because this is now, the whole thing is like a constant now. We need x and w to be like given to us so that we can have these two assumptions right here. That's the purpose of it. Square. If you take the log, negative log likelihood, you get this plus some constant right here. And notice this is proportional to if you were to multiply this whole thing by sigma squared. And let's, for convenience sake, pull out this 1 over 2, delete it, and then this plus c over here disappears. So it's a model parameter both of them. It is kind of weird. The way she defined it is kind of weird. Your data would be like P of Y X given W. Yeah, this is extreme. The way she defined it is like extremely weird. So unfortunately, I have to move on because I think we're almost at the halftime mark in 30 minutes. And I'm not close to being halfway. And this is proportional to this. Sigma squared over alpha norm W. And then what we can do is that we can let this be lambda. All right. And that's essentially how you prove that ridge is equal to map estimate. Because if you were to solve this, this would be equivalent to ridge. All right. And now the second part of it is what happens if alpha goes to, sorry, what did I write? What happens if alpha goes to infinity? Does anyone know? Remember, alpha is equal to, sorry, lambda is equal to sigma squared alpha. Yes, then your lambda is equal to 0. And if your lambda is equal to 0, then you basically just have map estimation. All right. So you have no regularization. So so why is this important? Notice that if alpha gets infinitely large, then we're basically evenly distributing the probability mass of this W vector. We're essentially just evenly distributing it because the variance is like infinitely large, right? So we're evenly distributing out. So every possible W has the same probability of being true. Does that make sense? So it was like a normal. Oh, that's not a normal. This is a normal. And then if your variance gets large and large and large, it becomes like a compressed pancake. All right. For this question, I think I'll just run it with you guys. This one, is this true or false? Oh, actually, I'll give you guys like 1 minute to figure out if this is true or false, because it does involve a bit of work. Wait, hold up a minute. How many slides are there? Oh, geez. Um, is this true or false? Mind you, this question is not a trick question. It's pretty quick. If you remember, you is it, are you sure it's false? Can you explain why? Hmm. Or is true, but do you know why it's true? It's the same logic as, actually, this is true. I'm just gonna tell you guys this is true. It's the same logic as one. So let me start with one really quickly. Maybe this will help you guys. Remember, when you're deriving your normal equations, you have like when you're trying to solve for beta 1 hat and beta 2 hat, your parameters, you had these following equations. This one, correct me if this is wrong. Remember, you had like something like this, right? And this is equal to 0. But then you also had, oh, did I write beta or W? I wrote beta. Oh, whoops. So this is not W, this is beta. Yeah. Yep. And the second normal equation was like this. Beta transpose, where beta is like your vector of your weights. X, um, let's say xj, where this is like index xi. And this is equal to 0. It comes from our, remember, our MSC loss function. MSC loss function, oh, sorry, is this summation of 1 over n yi minus beta transpose x vector squared. This is our MSC loss function, mean squared error. Taking the mean of the squared error, right? And then when you differentiate this with respects to beta 1 and beta 0, you get it is equal to 0, and you get these two normal equations right here. So using this, is this true or false? Actually, I already told you guys it's true because for one, you can for simplicity purposes, I'm gonna just write it like this: transpose x vector xi minus x bar. X bar is a constant, right? So if we distribute this summation, we get this is equal to summation of yi minus beta transpose x vector xi minus, remember, x bar is a constant, so you can bring it out. Then you get something, you basically get this inside of here. And mind you, this is 0 from this normal equation. This is 0. This right here is 0. Wait, sorry. This is 0 from this normal equation, and this is 0 from this normal equation. So that's how you show that the first one is true. Where does the second equation come from? It comes from differentiating it with respects to beta 1. Remember your slope. It comes from, I think it comes from chain rule. Because if you have y, sorry, this is not clear. Because this is for all. This is equal to, sorry, I'm letting it be arbitrary. So this is like the partial derivative of the MSE function with respects to beta j. And this is with respects to beta 0, beta naught, your intercept. Okay, perfect. So just to move on for the interest of time, I'm just going to give you guys the answers and probably leave this as an exercise at the end. So this is false. And if this is false, then this is also false. And to solve this, you would have to come up with a counterexample. I provided a counterexample in the solutions, which I'll post at the end of this meeting. So, yeah. And for this one as well, what you can do is that you should notice that beta 0 hat, beta 1 hat, they're constants, right? So what you can do is that you can distribute this with this constant. So you just get the summation of this times this constant, and that's just equal to 0. Whoops. Plus, you can pull out this constant, but then you have this summation times this xi, which is equal to 0. So in general, you have 0. Everybody good? Did everybody follow? Who here is confused? Which part are you confused about? 1, 2, or 3, or 4? I'll just show it. Okay. So, and by the way, this was a past exam question in C11, I believe, in the winter. Not in the winter. Anyways, last fall, I think. 0 plus, actually it's minus beta 1 xi. As a sum of the residuals by OLS properties. I'll get to you later. I gotta finish this. This is equal to, if you distribute this, get beta 0, because beta 0 is just a constant, times the summation yi minus beta 0 minus beta 1 xi. Then you have minus, remember, beta 1 is also, beta 1 hat is also a constant. Summation n, I equals 1, yi minus beta 0 minus beta 1 xi. Look at this term. Remember, this is one of your normal equations, so this is equal to 0. Look at this term. This is also part of your normal equation, so it's equal to 0. Isn't beta 1 a vector? The way I wrote it last time kind of put it in a vector. It was very confusing. But in this case, they're just variables. This is a constant because we already estimated them. This is our estimation. Use the terminology with set of beta. Yeah, just pretend it's a W. Yep. Because in the exam, she'll put like pretty convoluted notation. You guys have to get used to it. Let lambda 1, lambda minimum, and lambda maximum be the minimax eigenvalues of this matrix right here. describe what happens to your regression if the minimum lambda is significantly less than lambda max. Yes, you guys are correct. It is ill condition. And recall the condition number is given by, I think mathematicians give it like kappa, x tilde transpose. The condition number is equal to the lambda max, lambda min. So if this minimum is significantly smaller than your maximum, then this is going to blow up very big. Did you have to find eigenvectors and eigenvalues during the exams? Fortunately, no, we did not. We had to use them, but we did not have to find them. All right. So I think this is, yep, pray. Yep. Good, good, good. And the next question is, what happens to this if they're equal? What happens to the matrix itself? I'm talking about the form of the matrix if they're equal. I think this is an assignment question. I'm not sure. Very well conditioned. Yes. And can you think of the most well-conditioned matrix you can think of? Sure, it is orthogonal. Identity matrix, correct. Do you know why it's the identity matrix? Yes, it's the scaling of the identity matrix. Do you know why? Because, look, if all your lambdas are the same, x1, x max, if all your lambdas are the same, then that means, I think I'll prove this later, but then let's call this lambda. Then this is just the identity matrix scaled by the general lambda, where the lambdas all the same, right here. So yeah, x tilde transpose. Is this always the case? Yes. If maximum lambda is equal to minimum lambda, then of course all the lambdas are the same because all the lambdas are squeezed in between the max and min. So yeah, I think this is always the case. I don't see how this could not be the case, unless if you try to prove it. Anyways, suppose you are using rich regression to make predictions on a data set with low variance features. However, you find that your model gives, remember, high training error, whoops, and high testing error. Error, not accuracy, it's error. You notice that your regularization hyperparameter is what's causing the issue. How should you tune lambda? Yup, you should decrease it. And I think you guys already know the reason why. So I'll just move on. Oh, actually, I think I'll give you guys do you guys need a break? Like a 10-minute, 15-minute break? No, yes, sure. Okay, I'll give you guys, are we halfway through? This is, I got 3 more pages. Yes, we are quite literally halfway through, and we're at the perfect time mark to take the 10-minute break. Okay, perfect. If you guys have any questions or you want me to scroll up to some questions, just let me know and I'll do that. Or finish earlier without a break. Um, how do I create like a voting thing? Actually, let me try to poll. Huh. How do I create a poll? Oh, there it is. Where is it? Whoops. Yeah, I got no idea how to create the poll. I think Christopher has that ability, but I don't. Unfortunately, I don't have a poll. So can we get like a consensus on where we should take a break or not? Like just yes or no. Just from everyone again. Okay, perfect. It seems like everyone wants to take a break, so See you guys at 7:30. I'll give you guys 15-minute break. 7:30. So how will we choose which features is important? You would have to check its correlation. Do you guys not because you guys took B52, right? So you guys should be able to like calculate the sample correlation between the labels as well as the um actually I'm gonna show you on a whiteboard. This is not actually taught in C11. This is taught in like C67. But I'm gonna show you anyways, just in case if you actually need to do it. So recall your correlation coefficient, we call it rho, is basically like a measure of how similar, how linearly correlated two things are. So yeah, there's like a linearity assumptions. I'm pretty sure there's like other methods out there to check nonlinear relations, but this is one way. It's bound between -1 and 1. Sample correlation is defined as 1 over n minus 1, where n is the size of the sample. Your first variable minus its mean, yi. Your second variable, whoops, minus its mean divided by, yes, I will be covering gradient descent pretty thoroughly at the end. And the denominator is the sample variance of x and the sample variance of y times the sample variance of y. What is the sample variance of x? It's just xi, summation of this, squared minus n minus 1. So you'll basically have to check how correlated, and obviously you have to normalize your data so it's all on the same scale. So you can check how correlated your features are with respect to your labels, or actually your output, not your labels, because you can't really do this with labels. I think you can, but it's going to be a bit harder. But yeah, this is how you do it. This would not be covered in the exam whatsoever or in C11. This is just me showing you how you would do it anyway. What's the order thing you mentioned? So for a problem to be a regression problem, you require that the output space, I think she taught this, she mentioned it, it needs to have order and needs to be numerical. This one's a pretty obvious one because if it was like A, B, C, D, E, F, G, then you obviously can't do regression in it. Order is another important factor, and that was the purpose of the one of the questions I did. Order is important because once again, if we're trying to predict like the labels 1.2, 1.1, remember these are labels because we're trying to predict handwritten digits. 1.212, 4.2, etc., etc. Then obviously since these are labels, these have no ordering. So these are just like labels, right? We can't really compare like which one is greater than which. Do you see how this creates a problem when we're trying to put this into like the MSE function, the mean squared error, or try to even like calculate the X bar or sorry, the Y bar in the X, sorry, the Y bar. Labels, I mean like, okay, you get it. Yeah, perfect. That makes sense. Any other questions or is that it? Yeah, of course, they have to be numeric. Like they have numerical values. Say it right. Oh yeah, yeah. Like the handwritten decimal numbers are they are numeric, but they do not have order, and that's why it's not a regression problem. Think of this as like think of this as an isomorphic problem to like tracking handwritten alphabet. Okay, okay, perfect, perfect. You need to know how to differentiate them, and they're derivatives. I think that's like in like a sheet because you're gonna have to derive some stuff like the ridge regression stuff. Similar questions to that. That's why I got on my exam. You need to know like the derivative of like a vector, derivative of a matrix. But that's all of that is like given to you. That's probably going to be given to you. Otherwise, you have to memorize it. Just the basic ones covered in lecture though. Not the whole entire partial derivative of like a matrix. That's pretty crazy to remember. All right. I hope you guys enjoyed your break and we will move on. So right now we're halfway through the review seminar. How does KNN perform on very large data sets? Whoop- Whoops. Does anyone know how it performs on very large size data sets? Very expensive. Can you elaborate on very expensive? Like, what are the consequences of it being very expensive? Exactly. You have to find the distance of every point in basically every single point to find the k nearest neighbors. And that, as your data set gets very large, that takes a very long time. What's a Voronoi diagram? Oh, did she not mention what a Voronoi tessellation diagram was? Uh, oh, geez. I think it was in the notes, but it was basically like, because by the way, you will get a question like this. I got a question like this on, I think on my final exam, but since you guys are doing canon, a Voronoi tessellation diagram. Let me just show you guys. Voronoi tessellation. It's this. Try to find a good example. It's like this diagram, where like each of these regions represent what classification, what your thing will be classified as. So it could be like X or zero, X or O's in these regions. And trying to find some good images of it. Classification is on midterm. Oh, is it not? Oh, wait, you guys did cover. Oh shoot. Yeah, you're right. This isn't covered until classification. Oh yeah, you're right. You guys are right. Okay, you know what? We can just skip that question. We can skip this question. We did graded descent earlier though. Yeah, that's fine. That's fine. I have graded descent as the last question right here. These are some pretty decent questions. I think this one, and this one are they were on past exams. So, question two. Suppose you're trying to predict binary labels with weighted K and N using the weight function, this weight function. So basically like a radial weight function where sigma squared is a hyperparameter. So this is something you could tune. However, when you plot, oh, the Voronoi tessellation diagram, you find that your model underfits. So I think you guys did cover what it was. So just ignore this. So you somehow find that your KNN overfits, all right? So just two ways to counteract this. I think one way we already described. Yeah, just reduce K. There's a reason why I made this a weighted KNN problem. Can anyone figure out what we should do with this weight function? Think about this. If we increased, actually, if we decreased sigma, remember, this is a radial function. If we decrease sigma, we're putting more emphasis on closer points. Whereas as we make this grow larger, as this goes to infinity, listen here, if this goes to infinity, then this whole numerator goes to zero, and this e just becomes one. So there's really no weight. So that's what happens when your sigma gets very large. It evenly distributes out the weight. But if we make our sigma smaller, then it places more emphasis on closer points. I'm just going to give you an answer. So what we have to do is that we have to decrease sigma, basically make it more spread out. Actually, is that correct? Yeah, we have to, no, it doesn't make it more spread. It makes it more focus on closer points. And what that does is that creates sharper decision boundaries. So remember, it underfits, right? So let me give you an example. It has the same effect as if we increase it, if we make it more local. It finds more local points. So let's say we have a dot right here. Bigger sigma makes it more focal. It's the opposite. I think I misspoke, but bigger sigma makes it more um evenly spread out. Smaller sigma makes it more centered at a particular point because more weight on closer weight. So overfit's kind of offsets the underfit. You can think of it like this. Let's say we had something like this, correct? Let's say we use k equals 2. What if a point, let's say this region right here was the actual region of a dot, and everything else after here was like the region of the x. What if we had a point right here? If we use weighted k and n, oh, actually, let's make this k equals 3. If we use weighted k and n, it'll look at this point, but if it looks at this point, it doesn't matter because it's k equals 3. We're always going to see these 2 points, and it's going to dominate this point. So this whole region right here gets classified as X, but we want this whole region here to be classified as a dot. So that's kind of like the intuition of it. All right. Does anyone have any questions? Perfect. Next question. Which of the following is true? So let's start with the first one. K&N requires training time. Any suggestions? Any guesses? False. That is correct. It is false. Because, like I said, we have to retain our whole entire data set. You look at the data, you look at the given data only. Yes, exactly. In image denoising, increasing basis function width leads to underfitting. Any more guesses? Or sorry, any more answers? Think about what I discussed about, um, not sure which position we are at. So if you're looking at the given data and studying it, you're not training. There's a difference between training and inference. When we don't train KNN. We evaluate our answer like during inference time. So that's when it's like finding the nearest neighbor. That counts as inference time. We're not really training it and saving a parameter per se. So that's actually another reason why it's KNN is non-parametric because we're not really saving a parameter to do like regression um predictions and whatnot. But yes, you guys are right for number one. Increase width leads to less localization, which isn't good for denoising. How does I don't understand. Increasing the width means increasing the influence of each point of each basis function. Yes, that is true. Simpler model. I don't know if that counts as simple model. It makes it more. It spreads out the weight of each point more evenly per se. Does that make sense? If we decrease the width, then we have more emphasis. So it does not lead to underfitting. Sorry, if we increase the width, then it does lead to underfitting. So that is true. Question 3. Polynomial, sorry. So there's less emphasis on local regions if the width is too big. Yes. So let me just draw this out. So it kind of makes intuitive sense. Think about like a normal distribution, and then you just, because it basically is like an unnormalized normal distribution. And then you're like distributing out the width more evenly. Sorry. then as your width increases, you're basically distributing the variance out more evenly. So there's less weight. There's less weight at where the center is. But we're underfitting, increasing the weight just adjusts it to the right position. What do you mean by adjusting it to the right position? We are underfitting to better model. I'll get back to this question because I think we have to move on. So polynomial basis, oh, underfitting. No, I don't no, that's not the case. I think I have this was actually a past exam question and this happened to be true because if we increase the width, then we're basically spreading out more evenly. Yeah. Yeah, it's kind of weird. So I'm probably going to move on. Polynomial basis functions should be used over RBFs in image denoising because it's better at capturing local features. Is that true or false? Yep, it's the inverse. Yep, it's false. And that's because polynomial basis functions are better at capturing, it's better at extrapolating, whereas RBFs are the ones that are good at capturing the local features. KNN and regression are parametric. Yeah, extrapolating is a global fit. That's correct. It's false. KNN and this statement is false because KNN is non-parametric. That is correct. We'll skip this question because unfortunately, I don't think this was covered yet. So which one's true? Oh, let's see. I think it was just this one is true, but we were a little bit iffy on this. By parameters, we mean like to define the parameters by on like some type of training set. Does that make sense? Because in KNN, we're not really saving any parameters to make predictions. We just make predictions as is based on the data set. Whereas in regressions, we're saving like the parameters W vector or beta vector in order to do the predictions. That's what parameters are when we're saving some things that we learned. KNN, we're not really learning anything. We're doing the inference, we're doing the predictions during inference time. Perfect. So skip this question. How do you select the optimal number of basis functions to minimize loss without using validation sets for those who know? Any suggestions? Actually, I think I should have removed this. Yeah, you basically brute force it. So to be more precise on what brute forcing is, we basically just plot it, where this is like the number of basis function, and we're plotting it with respect to the accuracy. So usually you have like a plot of like the training accuracy. It's going to look something like this. This is the training accuracy. The testing accuracy would look somewhere like this if you get a good model, right? This is your testing accuracy. And then, sorry, this is with respect to the number based function. This is completely wrong. I was thinking of something else. Whoops. So let me restart this. So it'll actually look something like this. Your testing actually, as you increase your basis function, would look like this, whereas your testing accuracy, training accuracy, looks like this. So you would have to pick this point, and this is like your optimal number of basis functions. Is there a monomial basis specifically? Basis functions can vary a lot. Uh, what do you mean by that? I mean, it could be for any basis function. It could be like a radial basis function. It could be for polynomial basis function. This works pretty much for every one of them because if you increase the number of basis functions, you're basically increasing the complexity the same way. Yes, of course, it has to be the same family of functions when you add or decrease number of basis functions. All right, perfect, perfect. Next page. I'll give you guys 5 minutes to do this question. This is a probability. Why is accuracy decreasing by increasing number of basis functions? Oh, whoops. Whoops, 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 whoops. I think we can change this to loss. Here, loss. My bad. The graph would look completely different. It would look like this instead. It would look like this instead. All right, I'll give you guys 5 minutes to do this. So around 7:51. Also, I got a similar question to this on like a multiple choice in my term test one. So yeah. Recalling the question about experience, task, and performance, isn't task always going to be minimizing the total loss? That's we're talking about like in a general sense, right? The task is to essentially denoise the image. The experience is what we already experience, which is the original image, and the P is the performance measure, which is your MSE. So we're being very specific right here. So yes, in a way, it is going to minimize the task is technically minimizing the total loss, but by doing that, we basically denoise the image. Does that make sense? We have to be very specific when we say what the task is. And I think okay, perfect. All right, let's see. I'm gonna show the work for it. So, as someone said in the chat, yes, we're trying to predict whether we have disease. Yes, Bayes' theorem. If we tested positive, probability we have the disease. How do you do this? Simple enough. Bayes' theorem. P of D. Can anyone tell me what's going to be in the denominator? Actually, it's pretty long. I'm just going to do it. So it's going to be plus, give it D, E, D, plus P of plus. Also, correct me if I make a mistake anywhere in this calculation. All right, perfect. We are given the probability if we tested positive, given that we have the disease. So I believe that's 0.99. This is it 0.0001? I think it is. Yeah. And then we basically copy and paste it down here. However, for this one right here, for this one right here, this is equal to 1 minus P of plus complement, tested plus complement. Yes. So the question says, if you tested negative, given that you don't have the disease. So if we tested negative, same as plus complement, given that we don't have the disease, we're given this, but we're not given this necessarily. And what is this equal to? This is equal to 0.01. 0.01 times 1 minus 0.0001. Because remember, this is equal to 1 minus P of D. And like you guys said, it's equal to 0.98. All right. So yeah, the question is pretty obvious. Of course, comparing if we had no prior information if the test was positive or not, our likelihoods, our chances of knowing are like 0.001. The probability that we have the disease is this. But if we had knowledge, then this increases. So that's kind of like the power of prior knowledge right here. This describes the power of the prior knowledge. Our probability that we had the disease increases dramatically. All right. Next question. This one's a little tough. I'll actually give you guys 10 minutes for this one. Yeah, this part right here is pretty tough if you try to prove it. So I'll give you guys till like 8:05. I'll give you guys till 8:05 to do this. By the way, guys, I have a question. Did she say finite differences will be on the exam? Finite differences. That was in the lecture notes. It's like an approximation of the derivative for like a very small h, very small h. We can approximate. Okay, okay, but is it in the is it going to be in the exam? She went over it briefly. Did she say she's not going to include it in like the information sheet, if there even is an information sheet? Oh, I meant the notes. Yes, it's in gradient descent, chapter 10. She only mentioned it briefly. Hmm. I think just to be safe, I'll actually I'm not even sure because we might run out of time. This part is pretty long. So for now, I'll just omit finite differences because I don't think she's going to make you code up anything related to it, like write pseudocode. Yeah, of course. I just meant pseudocode because you might get asked to write pseudocode for gradient descent. That's like a very high probability. All right. So, can anyone tell me the three types of estimators discussed in lecture? Yep, exactly. Bayes, ML, and MAP. And which one of these are point estimators? MAP and ML. That is correct. How about can all three of them ever be equal? Sure. Can you explain why? If it's you mean uniform prior? Huh. Interesting. Yes, exactly. Yi Tong. Sorry if I butchered your name, but that is correct. If your likelihood is normal and your prior is uniform. So let me see. This one's pretty long to show. I'm pretty sure you guys can clearly see if your weights, what did I write it as? I didn't write it as anything. So clearly this can equal this under if your weight vector follows like a uniform distribution. So P of W is equal to 1. Then you just have that your posterior is proportional to this. And then you can just solve it as is. For the base, you kind of have to do a little bit more work. It's pretty complicated, so just hang on tight. Recall that the base estimate, mind you, the reason why I included this question here, even though it's complicated, is because this was shown on one of my exams. So for the base, recall that, should I use W or theta? I think theta would be easier to look at. Theta, given the data set. Remember, this is your base estimate. Theta base, right? Now, what we can do here is that we can find the distribution of theta given D and then find its expected value. So we can do that simply. We can do that by finding the distribution of the posterior. This is equal to, actually, this is proportional to P of D given theta. And like Yitong said, if our likelihood was normal, then this would be equal to some, I'm skipping a bunch of steps right now, but it'll be on the solution sheet. It'll be equal to this. Minus 1 xi minus mu squared 2 sigma squared. Mind you, this is a constant, so this is proportional to the exponent of a equals 1. From here, you can expand this polynomial to get I squared and distribute in the negative and the summation to get plus mu summation n is 1 xi, this, all divided by 2 sigma squared. How I got this? First, I expanded this polynomial, then I distribute the summation, right? So the summation of, and mu is just a constant, so the mu just comes out. Oh, shoot. Yep. In this case, our theta, we're trying to estimate mu. Sorry if that was a little unclear. Is everybody, is anybody confused by my sudden notation change? Okay. And then the last term is just mu squared. So the summation of a constant is just n times a constant. Then I just distributed the negative sign in. Notice this term right here is just a constant. So what we can do is that we can say it's proportional to, we can completely remove this constant right here. So how would you do this? Actually, let me make this more clear. Equal to xi squared 2 sigma squared times the exponent of mu. Actually, you can rewrite this as n times x bar minus n mu squared 2 sigma squared. And this is just a constant now. This is literally just a constant because there has no mu in it, your parameter that you're trying to estimate. And now this is just the exponent of, if you take the n out, this is equal to n, and then take the negative out as well, over 2 sigma squared. And then that becomes mu x bar. I'm wondering if we have a 2 in front of mu sigma psi, the second term in the numerator, if we have a 2, where? Um, Here, this term, if we have a 2, Yes, I think we would have yes, we would have two. Thank you for catching that. Yep. And then what I remember I did before was that I think I plussed x x bar squared minus x bar squared. And if you do this algebraic manipulation technique, you can get it, and after some manipulation, you get this is proportional to exponent this. Sorry if I'm skipping a lot of steps. I feel like we're going to run out of time when we get to gradient descent. All right. And notice this is just an a normal distribution that follows the normal x bar mu sigma squared over n. So let me write this more clearly. We have that our mu, given our data set, in this case is our theta. Sorry if I abuse notation here. Is similar to, sorry, it follows x bar this. And then finally, we just take the expected value of it. And then we know from expected values of normal, this is equal to x bar. And we did calculate that mu star map is equal to mu star ml, and this happens to be x bar. So this is a case where they're all equal to each other. All right. Suppose you have a massive data set sampled from a Gaussian distribution. You notice by plotting your data that the spread of the data is near perfectly spherical. What can you say about the covariance matrix of the Gaussian distribution? The key word is nearly perfectly spherical. Anyone want to take a shot at this? It's bivariate, normal. It's not necessarily bivariate. It's a 3D Gaussian, so trivariate. Covariance 1. Yes, Zubair, that is correct. It is isotropic, only diagonal. Yes, that is correct. It is isotropic. And the reason for this is that recall from the notes that if you have like a just a simple diagram, you have your like eigenvectors like this, right? If you all of your if you have like a spherically distributed data, then all of your lambdas are the same. So lambda 3 in this case. If all of your lambdas are the same, then sorry, as for let me show you this rigorously. This is not rigorous enough. But yes, all of our lambdas are the same. But if we have sigma, we know that sigma is symmetric, correct? So that we can apply real spectral theorem on this to get U transpose, the diagonal matrix, and U. Remember, your eigenvalues are all the same. Lambda 1 is equal to lambda 2 is equal to lambda 3. Let's call this lambda, all right? So what happens to our diagonal matrix? It becomes a scalar multiple of the identity, U. But then we can pull out this, then this just becomes U transpose U. But recall from linear algebra, this is orthonormal. So this just becomes the identity. So it becomes isotropic. Your sigma is a scalar multiple of the identity. So that's how you show it. Okay? All right. And finally, for the last slide, write pseudocode for gradient descent with backline search to solve this OLS problem right here. Do not use finite difference. Completely ignore this. How do I read? Yep, completely ignore this. Just do this. I'll give you, sorry, I'll give you guys like 10 minutes to do it. All right. I hope you guys had enough time to write the pseudocode for it. Anyways, I'll just give you the answer. So the first thing we need to do is that we need to define the function for our loss function. And that happens to be, since we're doing OLS problem, we have to use the MSE loss function. So let's see. Define E. You pass in the W vector right here. You initialize your sum as 0. For I, starts at 0 to n, do the following. When increment the sum, by this, x tilde I. And then we end the for loop. End for loop. And finally, we can just return the sum divided by n. Because remember, this is MSE. We need to divide by the n. All right. Next, we need to define the gradient function. Is backline search different from the algorithm on the slide? What did she call it? Sorry, give me a second. I just call it backline search. Yeah, she calls it line search. Yeah, this is just line search. Strange. All right. Interesting. So now we need to define our gradient function. So let's call it backtrack lines. Yeah, I think I had a typo on the slide. I mistaken the both for each other. It's just line search. Sorry about that. Maybe. And then let's say this is your gradient. And this is like an empty vector at first. Now we need to iterate through all of the W's. Mind you, this W is like an augmented. This W has been augmented. So it has like W1, WK, and then 1 right here. So for I starting at 1 to the length of W, so you want to iterate through all the W's, we want to do the following. I might have to. Is it okay if we just use pseudocode from the slide or to define the code as accurate as possible? I'm not entirely sure. You probably have to ask during the exam, but I'm just showing you how to do it as accurately as possible in case if it does happen to be the case that you need to do it as accurately as possible. All right. All right. So now you want to do this. You want to append the following. Remember, let's say the partial derivative of your MSE function with respect to WI. Remember, this is equal to 2 over n, summation n I equals 1, yi minus w vector transpose x tilde I. But then you need to multiply by x tilde I right here because of chain rule. All right. So we literally just put this whole thing in here. And you can do that easily with a for loop. And for. Then we want to return nabla, your gradient. So once we have all of this defined, we can finally move on to the actual gradient descent code. Initialize your initialized weight parameter. Yep, your weight parameter. Let epsilon be greater than 0. This is for your stopping condition. And initialize lambda because we're using line search. Let's I initializes to 0. Mind you, this is initialized randomly. Whereas these ones, we have to pick a certain value for them. While, whoops, your objective function has a small change. Sorry, has a change that's bigger than our threshold because we want to end the gradient descent algorithm when this becomes sufficiently small. Do the following. We don't want this to run forever. Let's actually, no, no. Define del as your gradient with your objective function in W, I passed into it. Now you want to let your lambda, let's get to 2 lambda, while, it's another while loop, while, and this while loop checks if you overshot, and it keeps on having the lambda, cutting that lambda in half if you overshot it. That way, you can always ensure that your objective function is decreasing every time you do a gradient descent step. You want to have your lambda. And while. And then finally, oh, where's my mouse? Right here. All right. You want to set your next value of your parameter equal to the updated value right here. And then you increment I plus 1. End the while loop. And yeah, that's how you would do it. I'll have a more sophisticated solution posted. Actually, I don't think I'll be able to post the solutions in the chat. I'll just send it to Irene, and because my solutions had a lot of mistakes in it. But yeah, I'll send it to Irene, but I'll post the slides at the end. All right, next question. Which of the following is true? Gradient descent always converges to the optimal solution. Is this true? False. Can you explain why it's false? Yep, that is correct. It can oscillate around, so it doesn't always converge to the optimal solution. The learning rate, the next one, the learning rate dictates the rate of convergence. True or false? Can you explain why it's false? Yep, Zubair, you are right. This is true. If you have a smaller learning rate, then it takes your gradient descent algorithm much longer to converge. Whereas if you have a large learning rate, it converges much faster, but there's always the trade-off that it can always oscillate. And yes, this was a past exam question, and the correct answer is true. Should we increase the learning rate if our objection function increases? True or false? Can you explain why it's false? Yes, that's correct. If we increase, then, sorry, if our objective function increases, then that means we overshot. Why? Well, the gradient descent algorithm always points, your gradient always points out the steepest descent direction. So if your lambda is like very large, then it will overshoot, increasing your objective function. So you need to decrease your learning rate. All right, and the final question. Gradient descent is deterministic, true or false? Does anyone know what deterministic means? Yes, that's correct. Gradient descent is, oh, you were answering for deterministic. But yeah, gradient descent is deterministic because you initialized all of your parameter, all of your conditions to start. Let me just show you. You initialize everything in beforehand, right here. So by that, it's you can always determine the final outcome. It's not random. Yeah. All right, next question. You perform simple gradient descent on a smooth, that's important, a smooth, non-convex objective function, and through each iteration, your objective function oscillates around a high value before converging to the function's absolute minimum, so the global minimum. You decide to add backline search, but you find your objective function converges at a significantly higher value than before. What could potentially be the issue? There's actually two potential issues here. Can anyone think of the first issue? Mind you, it converges. So that means we found a point at which the gradient is approximately zero. However, the point of convergence that we found is a lot higher than the one we had before. The question is asking local minimum, not convex. Exactly, yes. It has a local minimum that is not the absolute minimum. So I'll give you a really big hint here. I don't know if the question was valid to begin with, but let me just show you. So for a non-convex function, mind you, this is an example of a convex function. So like any point, for any point you pick, you can always draw like a straight line such that the area between the curve and the line right here is like contained within the curve. This is kind of like an unrigorous definition of convex, but this is just to give you an idea of what convex is. An example of a non-convex function is like this. So in this case, if our learning rate is really high, let's say we have this point, then it jumps to this point, and then it could jump here, here, and then to the local optimum. If our learning rate's high, if we decrease the learning rate, it could jump here, here, here to the to the local minimum. So this is significantly higher than what we had previously. All right. Another issue. Can anyone think of another issue? Oh, sorry. Yeah, another potential issue. So Yitang was correct about it being a local minimum. What are the other cases where the gradient is zero? Saddle point. There you go. So the same logic. If you have like a saddle point, it can also happen at saddle points as well. So if your learning rate is very small, it could be like this, and it converges to the saddle point, which is very, very bad because this is not a local minimum nor a global minimum. All right, perfect. And you please give an example where the algorithm is not. Oh, sorry, did I say it was false? I meant it was true. Gradient descent is deterministic. Sorry, did I say it was false? It is not deterministic if you're using like stochastic gradient descent. Yeah, it's true. I said it's true. Gradient descent is deterministic because you already defined everything. Yes, it is deterministic. If we don't make if we don't make like the initialization random. Yeah, but that's still deterministic because we're having the learning rate. We're cutting it in half, right? I think you guys are thinking about stochastic gradient descent, but that's way beyond the scope of CSCC11. Anyways, and finally, for the last question. Oh, we're just on time. I'll give you guys 10 minutes to do this question. It's a pretty quick call. Stochastic gradient descent was mentioned in the lecture. Oh, was it? Oh, shoot. Oh, dang. Alongside mini batch. Oh. Well, unfortunately, I did not know that because I was uh, going solely off of the notes as well as what I experienced last semester. Yeah. Sorry about that, guys. But yeah, stochastic gradient descent is, as its name is suggests, it's stochastic, so it's random. So it's non-deterministic. Anyways, for this question, just I'll give you guys until 8:50, 8:51 to do this. Yeah, I'll give you till 8:51 to do this, and then I'll take it up. Mind you, this is a past exam question in, I think, C11 or 311. Uh, sorry, give me a second. I need to open it up in another. I'll see if I have time to go over them because I have to go right after this review seminar. Zubair, unfortunately, I don't think I'll be able to help you with these questions just because last semester when I took C11, we didn't really cover batch gradient descent and batch gradient descent, stochastic gradient descent, and mini batch. Yeah. I mean, I could give it a try, but I don't think I'll give you like good answers. Yeah, lambda is just the regularization coefficient. I pulled this straight from either C11 or 311 past exams, so the notation is a little bit weird. think it should be a good time for me to cover it right now. So I'll cover the solution and let me know if you got the same answer. Okay. Whoops. All right. So first we need to find the gradient of the objective function evaluated at the initial parameter. Because we need to find, we need to find this, right? To find this. But your learning rate, then your gradient evaluated at the initial parameter. So we need to find the gradient. This is equal to the gradient of, probably need more space. It's equal to x tilde w vector minus y transpose x tilde is equal to this. All right. The next step is essentially just to simplify this. So we have, by distributing in the transpose and then distributing the terms, we get w vector transpose x tilde transpose x tilde w vector minus 2w vector x tilde transpose y plus the regularization. All that evaluated at w, 0. And now, just take the gradient of this. You'll get 2x tilde transpose x tilde w minus 2. Oh, this w is supposed to be transposed. Then you have x tilde transpose y plus 2 lambda w vector. Evaluate this at w vector 0. And now if you plug in, because we have x tilde right here. We have x tilde. We have w0, right? So we just plug it in. We just plug in w0 into this equation. Y plus 0, like that. And then you just plug everything in. We're given x tilde, we're given this, we're given the learning rate. Actually, we don't need the learning rate in this case, but we're given y. So we just plug everything in, and you should get, please correct me if I did the matrix multiplication incorrectly, but it should be this. All right. And now you plug this into this equation right here. You're given your alpha, you're given W0, so you should get W1 after plugging everything into this equation. W1 should be equal to 0.123.96. All right. And now, since we want W2, right? We want W2. Want W2. So we just find, um, actually, we were already given the equation of the gradient. So we can just plug everything back into there. So we have to find the gradient evaluated at W1. And that's just simply by using the same equation we derived right here, except replacing W0 with W1. plus 2 lambda W vector 1 right here. And you should get the value negative 275.44, negative 590.32. And then finally, you said your W2 is equal to W1 minus alpha, and then the gradient evaluated at W1. You're given this, you're given that, and you also derive W1. So you can just plug everything in to get 16.344 0.432. And that's your final answer right here. And I think that's it for the review seminar. And we just ended in time. Perfect. All right, here are the sources of the questions. I'll post the slides. I'll post the slides in the chat right now. Whoops, no, that's a screenshot. All right. Well, I guess that's it. Thank you guys so much for coming to this review seminar, and I wish you guys the best of luck on your exam. I know you guys got this. As for your questions, yeah, no problem, Zubair. As for your question that you sent me, I'll do my best to assist you on this. Um, Also, all the solutions posted. I'll send I will post it on AMACSS once I fix all the mistakes. Sure, no problem, Samuel. And I'll send it to Irene as well, because there's a couple of mistakes on the solutions. All right. I'll help Zubair with this question, and I'll see you guys later. Thank you guys so much for coming.